Sketch the graph of the following function and identify all the properties that apply. In this example, we are working with the function f of x equals x squared. So let's start by sketching that graph. We're going to sketch it by plotting points. I'm going to choose the standard set of x's, -2, -1, 0, 1, and 2. And I'll substitute that into our equation y equals x squared. -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So now we have 5 ordered pairs that we're going to plot. We have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So we can see the shape of this graph is a U-shaped graph. We'll connect these points, and this is the graph of a parabola. And now we want to check to see if any of these properties apply. So we'll start with the first property. The first property says that the range of our function is -infinity to infinity. So I'm going to use my ruler to identify the range. The actual range doesn't start until we get to this vertex at 0, 0. So our range actually starts at 0 and goes to infinity. And so I would not select property A. The next property is referring to the domain. The domain of the function is -infinity to infinity. So let me hold my ruler vertically, and I can see because of this arrow that the domain will start at -infinity, and because of this arrow it will stop at infinity. I can also keep in mind that x squared is a type of polynomial function, and all polynomials have a domain of all real numbers, so I would select property B. The next question, or the next property, says that our function is an odd function. Now, for a function to be odd, it needs to have origin symmetry. So I can look at this graph, and origin symmetry is when you have a mirror image over the origin, which is 0, 0. So when you have origin symmetry, you should have opposite quadrants. Now let me highlight some opposite quadrants. So this is quadrant 1. And then you should have a mirror in the opposite quadrant of quadrant 3. That's where you would have origin symmetry. You can see that there's a piece of the graph in quadrant 1 and no piece of the graph in quadrant 3, so we don't have a mirror image. And so that means this function is not odd, and I would not select that property. The next property mentions being increasing on the interval from -infinity to infinity. Now, as I analyze this graph, if I trace this graph starting here, I can see that my function is decreasing on this portion of the graph. So it is decreasing along this section. And this statement says it is increasing from -infinity to infinity. That would be over the whole domain. So since this function is decreasing on a portion of the graph, it can't be increasing on the whole domain. So we would not select this property. The next property says that this function is a linear function. A linear function has an equation with x to the first power and also has a graph that is a straight line. So we know that this is not a linear function. So I would not select that property. The function f is an even function. That's the next one. And even functions will have y-axis symmetry. So when I'm looking for y-axis symmetry, I'm looking to have a mirror image that goes over the y-axis. So I'm looking for a mirror, everything on the left to be a mirror of what you see on the right. And you do see that with this graph. You can see in quadrant 1 here, I have a mirror, and of that in quadrant 2. So this function does have y-axis symmetry, and we can call it an even function. And then the final statement says none of the properties apply. I would not select this one because I have selected a few of the properties above. So we've identified properties that match this particular function as having a domain of all real numbers, negative infinity to infinity, and this function being an even function. Use the graph of the known basic function in a combination of horizontal shifts, reflections, and vertical shifts to sketch the function. The function we'd like to graph with transformations is g of x equals negative x cubed plus 3. First, we're going to recognize what our base function is, or basic function. And that is going to be y equals x cubed. So I know it's y equals x cubed because of the cube here. So I need to know what that basic graph looks like. I know it passes through 0, 0. And at 0, 0, it has sort of a little squiggle in the graph. But mostly we see the left end quickly going to negative infinity and the right end going to positive infinity. Then we want to look for the transformations in this particular equation. In this equation, we see this negative that's out front, that's one transformation, and then we have this plus 3 that's added, and that's another transformation. Now, with my transformations, I need to have them memorized, and whenever I have a negative multiplied, I'm going to have a reflection. When the negative is multiplied on the outside, like this one, it's a vertical reflection. So that's a reflection over the x-axis. Whenever I have adding or subtracting, that's when I have a shift. This plus 3 is happening outside of the base function, so I know it's vertical. When it's outside, it's vertical. And vertical is either up or down. Because this is a plus, it is up 3. So what I am going to pay attention to is, remember that the base graph crosses through 0, 0. So a reflection is not going to affect that 0, 0, but a shift up will affect that 0, 0. So I'm going to shift that point up 3. And then the reflection will change this portion that goes up. It will make it reflect down. And this portion that is down, the reflection will make it go up. So that gives us a sketch of our graph of g of x equals negative x cubed plus 3. So that gave us our basic graph reflected vertically and shifted up 3. Give the rule that describes the piecewise defined function in the graph below. So we're given this picture. You can see that we have two separate pieces, and we want to be able to write the piecewise defined function that represents each one of these pieces. So I'm going to lay out the format of this piecewise defined function first. And the first thing we've already noticed is that it is two pieces. So that means that we're going to have two equations. So I'm putting a block here to represent the two equations, and then each equation will have a condition for that equation. The condition is telling us when to use that equation. So let's label these boxes with 1, 2, 3, 4, and I'm going to fill out boxes 2 and 4 first because we can easily recognize the conditions. So for box 2, and let's label this one with equation 1 and this one with the equation 3 there. What goes in box 3? So for that equation that I've labeled with number 1, I know that the conditions are that it's going to start with an x of -8 and end with an x of -2. So x is going to be in between -8 and -2. Both of them have filled in dots on the end, which means the endpoints are included. So then for the other equation that I've labeled with number 3, I'm going to find the conditions for that equation. And I can see that this line starts with an x of -2. This time there's an open circle on the end, and this arrow indicates that it goes on forever. So my x is going to be greater than -2, and I'm not including an equal to on this one because that endpoint is not included. So those are the conditions for the two equations. Then I want to find the actual equations. So let me erase these markings. And I noticed that this first one, I labeled this with number 1, is a straight line. I'm going to be able to find the equation of the line by using these 2 points. So I've got 1 point. I've got 1 point being -8, -3. And the other point is, looks like they've labeled it right here for me. It seems a little bit far away, but that's the point -2, 3. And with those 2 points, I'm going to be able to calculate the slope and then find the equation of the line. So my slope formula is y2 minus y1 over x2 minus x1. So let's label this with x1, y1, x2, y2. And I'll calculate the slope to be 3 minus -3 over, excuse me, -2 minus -8. And in the numerator, that will give me 3 plus 3. In the denominator, that's -2 plus 8. And we get 6 over 6, which is 1. So this equation has a slope of 1. And then I'm going to use y minus y1 equals m times x minus x1. This is called point slope form. and this will allow me to get the equation of that line. So I'll use this point and this slope to find the equation of the line. That's y minus -3 equals 1 times x minus -8. I'm going to rewrite this, solving for y. That's going to be in slope-intercept form. So that's y plus 3 equals x plus 8. I'll subtract 3, and that gives me y equals x plus 5. So that gives me the equation for the line. So the last thing I want to do is find this equation here. I notice that this is a horizontal line, and the equation of a horizontal line is y equals whatever the y value is, and you can see that the y value is 5 from this ordered pair, and you also notice that all of these other ordered pairs have a y of 5. So that's y equals 5 for the other equation, the one I've labeled with number 3. And now we've found everything, I'll go ahead and write out our piecewise defined function. Our piecewise defined function is f of x equals x plus 5, and we're going to use that when x is in between -8 and -2, and 5 when x is greater than -2. So that's our piecewise defined function. On this question, we're given two graphs on the same coordinate plane. We're given the graph of G, which is this straight line here, and we're given the graph of F, which is this parabola. And we have some questions related to those functions involving the operation of composition. So in part A, we have F composed with G of 1. And what we know about the operation of composition is that one function gets substituted inside of the other function. So this is going to be F of G of 1. So we substitute G inside of F. The function that is after the composition symbol gets substituted inside of the one that's before the composition symbol. Now on the inside, we now have G of 1. This is information that we're going to be able to get from the graph. These symbols, G of 1, tells me that x is equal to 1, and I'm looking for G of 1, which is I'm looking for the y value. So on the graph of G, I'm looking for an ordered pair that has x equal to 1. So right here is where we have the point, the ordered pair 1, 3. So I know that G of 1 is equal to 3. So I'm going to replace that G of 1 with 3. And now I have the symbols F of 3. And I know that x is equal to 3. And I'm looking for the y. Now on my graph of F, I'm looking for an ordered pair that has an x of 3. So that ordered pair would be right here. That is on the graph of F, and it has an x value of 3. So we have 3, 0 for that ordered pair, and I know that f of 3 equals 0. So I figured out that f composed with G of 1 is equal to 0. Now the rest of the problems are very similar. In part B, I want to find G composed with f of 2. So we're going to rewrite this with the understanding that composition is substituting one function inside of another function. So this is G of f of 2. And I know that x is equal to 2, and I'm looking for a y. So on the graph of f, this ordered pair right here would be 2, negative 1. So f of 2 is negative 1. I'll replace f of 2 with negative 1. Now I have an x of negative 1, and I'm looking for the y. So on the graph of G, this point right here has an x of negative 1 with a y of positive 1. So G of negative 1 is 1. So we figured out that G composed with f of 2 is 1. We'll move on to the next example. We have part C, G composed with G of 0. And then we'll rewrite that, understanding that the operation of composition is substituting one function inside of another function. On the inside, we have G of 0, so we're looking for an x of 0, finding that y. Right here, we have an ordered pair that is 0, 2. So G of 0 is 2. We'll replace G of 0 with 2. And now we need G of 2. So we have an x of 2. We're looking for the y. And on our graph, G of 2 would be right here. And that ordered pair would be 2, 4. So G of 2 is 4. So we were able to figure out that G composed with G of 0 is 4. All right, moving on to part D. We have f composed with f of 4. That's f of 4. So inside we have f of 4. That's an x of 4. We're looking for the y. And over here on the graph of f, we do have an ordered pair that is 4, negative 1. So f of 4 is negative 1. We'll replace f of 4 with negative 1. And now we want to find f of negative 1. We have an x of negative 1. We're looking for the y. So f of negative 1 would be right here. We have negative 1, negative 16. So f of negative 1 is negative 16. So moving on, we have the next example. This one is a little bit different because we have a chain of compositions. And I just apologize for a second here. I wanted to write the final answer for this. F composed with f of 4 is negative 16. Okay, so going back to part E, we have a chain of compositions, and what happens is we end up embedding them inside of one another. So F is the one on the outside, then G on the inside of that, then F on the inside of that. So on the inside, we want to find f of 3. We've already identified f of 3 to be 0. So we can replace f of 3 with 0. That's f of g of 0. We've already identified g of 0 right here to be 2. So we have f of 2, and we've already identified f of 2 to be negative 1. So we found f composed with g of f of 3 to be negative 1. On our last part, f, we have g composed with f composed with g. Remember, composition is substituting one function inside of another function. This time g is on the outside with f on the inside and g on the inside of that. So we want to find g of 0. G of 0, we've already found that right here. That's equal to 2. Then we want to find f of 2. We've already found that. It's right here. That's negative 1. We have g of negative 1. And we've already found g of negative 1 to be right here, which is 1. So we have g composed with f composed with g of 0 being 1. For this question, we want to find the equation of all horizontal asymptotes, if any, of the rational function. We're working with the function f of x equals 6 over x plus 9. Now, the actual math or calculation involved in finding horizontal asymptotes involves calculus. Since we're doing this in an algebra class, what we're going to do instead of the calculation is that a bunch of scenarios or cases have been summarized for us, and we're going to memorize those different cases and be able to identify the horizontal asymptote from that summary. So we do have a little bit of memorization to do to be able to answer these type of questions. So what we need to do is know what the cases are. And in our cases, the first one is that the numerator degree is smaller than the denominator degree. In the next case, the numerator degree is equal or the same as the denominator. In the third case, the numerator degree is bigger by 1, bigger than the denominator degree. And in the final case, the numerator degree is bigger by more than 1. So in order for us to figure out which case we're working with, we have to know the degree of the numerator as well as the degree of the denominator. Now the degree is going to relate to the power on x. So for our denominator we have x plus 9. So let's analyze this. We have x plus 9. Each term has a degree. So this term has a degree of 1 because the power is 1. This term has a degree of 0 because there is no variable. And then the degree of the overall polynomial or denominator, we're going to take the highest of those degrees. So the degree of the denominator is 1, and we call that m. Now for the numerator, we have 6, and the degree of something without a variable is going to be 0, and it's the only term, so we know that the degree of the numerator is 0, and we call that n. So we can see here that the numerator degree is smaller than the degree of the denominator. So n is less than m in this case, and that's usually how we label this instead of with words with symbols. The degree of the numerator is smaller than the degree of the denominator. So our function is in that first case, and what we do is we memorize in that first case that the horizontal asymptote will be y equals 0. Anytime the degree of the numerator is smaller than the degree of the denominator, the function has a horizontal asymptote of y equals 0. Now, in the other cases, you have no horizontal asymptote if the numerator has a bigger degree. So in both of those cases, the numerator degree is bigger and there's no horizontal asymptote. And in the case where they're equal to each other, you have a horizontal asymptote, and you have to do a little calculation. It's going to be y equals the ratio of the leading coefficients. That's an LC, leading coefficients. So to just put a final point here, for this particular example, because the degree of the numerator is smaller than the degree of the denominator, this particular rational function has a horizontal asymptote at y equals 0. On this example, we want to find the equation of the horizontal asymptotes, if any, of the rational function f of x equals 7x squared minus 5x cubed over 6x cubed plus x squared minus 9x plus 7. So when we're finding horizontal asymptotes, as we've said before, the math behind finding horizontal asymptotes involves an operation called limit, and that is a calculus concept. Now, since we're in an algebra class, we're not going to do the calculation. The rules have been summarized for us into 4 cases, and we're going to find the horizontal asymptote with a little bit of memorization of what those cases are. So what we're going to do is we're going to identify the degree of the numerator, which is n, and the degree of the denominator, which is m, and we're going to compare those numbers to each other. And that's going to give us the 4 cases. So the first case involves n being smaller. In symbols, we write that as n being less than m. The second case involves the 2 degrees being equal to each other. So n is equal, n equals m. The third case involves n being larger than m, but by only 1. So n is bigger by 1. And symbolically, I would write that as n being m plus 1. N is 1 more than m. And then the last case is n also being bigger by more than 1. And symbolically, we write that as n is greater than or equal to m plus 2. So these are the 4 comparisons that we can come out with. And then we've got to memorize what the horizontal asymptote is in each one of these cases. Maybe I can make this a little bit neater with a chart. So in the first case, when the numerator is smaller, you're going to have a horizontal asymptote right along the x-axis, which is the line y equals 0. In the second case, when the degrees are equal to each other, your horizontal asymptote is going to be y equals the ratio of the leading coefficients. In the third case, we have no horizontal asymptote, and in the fourth case, we have no horizontal asymptote. So you may be wondering why we would separate those two out. And the reason is because there is a different type of asymptote called an oblique asymptote or a slant asymptote. And when your numerator is bigger by 1, you do get this other type of asymptote. So the oblique asymptote is a line, y equals mx plus b. And that is, you can find that using long division. Okay, so now that we understand the different cases, we need to identify the degree of our numerator and the degree of our denominator. So starting with the numerator, we have 7x squared minus 5x cubed. And if we look at the individual terms here, we can identify the degree of an individual term, and that degree is the power on x. So we have 7x squared has a degree of 2, and 5x cubed has a degree of 3. And then we identify the degree of the whole expression to be 3, and that is the highest of the degrees. So we now know that n is 3. The degree of the numerator is 3. But then we're going to look at the degree of the denominator. So our denominator is 6x cubed plus x squared minus 9x plus 7. We can look at the degree of individual terms. The degree of 6x cubed is 3. The degree of x squared is 2. The degree of 9x is 1. And the degree of 7 is 0. There's no variable, so the degree is 0. Then we look at the whole expression, and the degree of the whole expression will be the highest, which is 3. So we've identified the degree of the denominator to be 3. And now when we compare the degree of the numerator to the degree of the denominator, we can see that the two degrees are equal to each other. And now that we know that we're in the second case, we're going to be able to find the horizontal asymptote by using the ratio of the leading coefficients. Now, that language might be a little bit confusing because it uses the word leading, L, for leading, but leading doesn't actually mean first. Leading is only first when you write your terms in descending order. This numerator has not been written in descending order, so you might, by mistake, identify 7 as the leading term, and that would be wrong. Your leading term is always paired with the highest degree. So your leading coefficient from the numerator would be -5, and your leading coefficient from the denominator would be 6. And the line y equals -5/6 is the horizontal asymptote for this expression. So just to go back to the original for a second, this is the highest degree term from the numerator, and this is the highest degree term from the denominator. We're going to use the ratio of those coefficients. So this one was kind of tricky because they wrote that numerator out of the typical order, which we call descending order. And so you might have, by mistake, identified the wrong leading coefficient. On this example, we've been given a picture of two graphs. We have the graph of f written in red here. This is a very interesting graph. It has a feature you may not have seen before. This is called a cusp. It's where it kind of comes to a point and curves out. Looks kind of similar to an absolute value graph, but you can see that the line is curvy instead of straight. In this blue graph, we have a straight line, and that is labeled G. So this curvy one with the cusp is labeled F, and the straight line is labeled G. And on the left here, I have some examples that we're going to work through. We have f plus g of 16, and we're going to simplify this. What this notation wants us to do is to evaluate f at 16, evaluate g at 16, and then add the results together. So I want to identify an x value of 16 on f and an x value of 16 on g. So over here on the right hand side, I can identify on the graph of g a y value of 3, so that's 16, 3. And then on the graph of f, that looks like 16, 4. So I'm identifying the y-coordinate on both of these. So f of 16 would be 4, g of 16 would be 3, and I want to add those results together to get 7. So let's continue on to the next part. We have f minus g of -16. And I'm going to evaluate f at -16, evaluate g at -16, and then subtract the answers. I'm subtracting the answers because of the subtraction in my function notation. So I need to identify an x value of -16 and find the y for f. An x value of -16 on g and find the y. So over here on the left hand side, I've got this ordered pair, which is on g, and that is the ordered pair -16, 1. And this value right here is on the graph of f, and that is -16, 4. So f of -16 is 4. G of -16 is 1, and I want to subtract those values, and that gives 3. In the next example, I want to find g times g of 16. This is the same thing as g of 16 times g of 16. We've already identified g of 16 to be 3. So this is 3 times 3, which is 9. So we notice that we're doing multiplication here because there's multiplication in the function notation. And then finally, we want to do f over g of 1, and that is f of 1 divided by g of 1. So we've got division here. We're doing division of our individual functions. So f of 1 would be right here. This is the ordered pair 1, 1. And g of 1 doesn't look like it gives us a nice number. Okay, so what I've noticed here is I wrote the problem wrong. I wrote this as f over g of 1. It should have been f over g of 16. So let me make that correction. So this is f of 16 divided by g of 16. And we've already found f of 16 to be 4 and g of 16 to be 3. When we divide those, we get 4/3. So f divided by g of 16 is 4/3. Find the function g composed with h and simplify. G of x is equal to 7 over x plus 6, and h of x is equal to the square root of x plus 10. Now we want to find g composed with h. Now this operation of composition means substituting one function inside of another function. So g composed with h of x has the meaning of g of h of x. So you can see that the h of x is inside of the parentheses of g. So to calculate g composed with h, we're going to substitute h of x in for that x. So this is going to give us 7 over the square root of x plus 10 plus 6. Now this is an acceptable way of writing our answer, 7 over the square root of x plus 10 plus 6. But there are some simplifications that you might not be aware of that you could do if you wanted to. And one of those simplifications is called rationalizing the denominator. And what the rationalizing the denominator refers to is basically not having this radical in the denominator, the square root in the denominator. So if you wanted to do that simplification, you would start off with your answer of 7 over square root of x plus 10 plus 6, and you would multiply by what's called the conjugate of your denominator. And the conjugate is just changing this one symbol here, this plus to a minus. And we're going to multiply that on the numerator and denominator. So in the numerator, I'm going to write it as 7 times the square root of x plus 10 minus 6. And in the denominator, I'm going to perform the multiplication. When I perform the multiplication, when I multiply these two square roots together, it works out to be x plus 10. When I multiply the outside with the inside, because we use the opposite sign, those two middle terms end up canceling each other out. And then I'll multiply the last and get a minus 36. And I'm going to go ahead and multiply the numerator. That's 7 square root of x plus 10 minus 42. And I'll combine the like terms in the denominator. That's x minus 26. And this is equivalent to what we had up here, just in a different format called rationalizing the denominator. Evaluate the composite function given that f of x equals 5x plus 4 and h of x equals square root of x plus 3. We want to find f composed with h of 1. So I'm going to show you two different ways that you can get to this answer. So the first way has you doing kind of a two-step process. And the first step in the process would be that you would build the function that's being described right here, f composed with h of x. Then once you've built that function, then you're going to do your substitution, which I always say plug. So that's when you're going to plug in or substitute in that value of 1. So that's the first way I'm going to show you how to do it. And the second way is going to follow the symbols. So let's start off with the first way. So we're going to start by building this function that's being described here. So I want to do f composed with h of x. This operation of composition is substituting one function inside of another function. So we're substituting h inside of f. So we're going to substitute this square root in for that x. That's going to give us 5 square root of x plus 3 plus 4. And there's not really any major simplification we can do here, so we're going to stop. So we've built the function. That was step 1. Then we're going to evaluate or plug. That's f composed with h of 1. So that means in place of this x, we substitute a 1. And that's going to be 5 square root of 1 plus 4 plus 4. And we'll simplify square root. Excuse me, I made a mistake there. I wrote, instead of the 3, I wrote 4. So let me fix that. So let's change that to a 3. We get square root of 4. Square root of 4 is 2. 5 times 2 is 10. And 10 plus 4 is 14. So we've gotten that f composed with h of 1 is 14. So that's one way to get your answer. The second way is going to be to follow the symbols that you have. So we have f composed with h of 1. And we want to keep in mind that this composition is substituting one function inside of the other function. So I can rewrite it in this way, f of h of 1. And now on the inside, I'm going to calculate h of 1. h of 1 is evaluating h at 1, plugging a 1 into h. So that is the square root of 1 plus 3. And the square root of 1 plus 3 is the square root of 4. And the square root of 4 we know to be 2. And then we're going to work out f of 2. That's substituting a 2 inside of f. So 2 in for that function there. That's 5 times 2 plus 4. That's 10 plus 4, which is 14. So we were able to work out F composed with H of 1 to be 14. So now you've seen two different ways that you can work out this evaluation of a composite or composition of functions. A toy rocket is shot vertically into the air from an 8-foot tall launching pad with an initial velocity of 104 feet per second. Suppose the height of the rocket in feet t seconds after being launched can be modeled by the function h of t equals negative 16t squared plus v naught t plus h naught, where v naught is the initial velocity of the rocket and h naught is the initial height of the rocket. How long will it take for the rocket to reach its maximum height, and what is the maximum height? So we're given this function, h of t equals negative 16t squared plus v naught t plus h naught. And we're told that v naught represents the initial velocity, and we're told right here we have an initial velocity of 104 feet per second, and we're also told that h naught represents the initial height, and over here we're told that the toy rocket is shot vertically into the air from an 8-foot tall launching pad. So that represents the initial height. So we're going to be able to substitute these values into the model for this specific situation. So our function is really negative 16t squared plus 104t plus 8. Now the goal of this question is to identify how long it will take to reach its maximum height and what is the maximum height. So what we notice about this particular function is that this function is a quadratic. Because of the leading coefficient being negative, that quadratic will have the graph of a parabola that is oriented down, and the highest y value, which represents the height, will be at the vertex. The maximum will be at the vertex. So the key to finding how long it takes to get to the maximum height and what is the maximum height is to find the vertex. Now we do have a formula for finding the vertex, and we can find h, which it's a little bit unfortunate that the writers of this question chose to use h for height, because we typically use h for the x-coordinate of the vertex. So these two h's represent height, and this h is the x-coordinate of the vertex. Okay, so just wanted to label that so there was no confusion later. So the formula, the vertex formula, is negative b over 2a. A is the coefficient of the squared term, b is the coefficient of the linear term, and c is the coefficient, or c is the constant. So we're going to be able to find that vertex by doing negative 104 over 2 times 8 . Excuse me, I made a mistake there. That should be 2 times a, not 2 times c. So c is a negative 16. And 2 times 16 is 32, so we've got a negative 32 in the denominator. 104 divided by 32 would be 3.25. We found the x-coordinate of the vertex. The x-coordinate in this particular problem, we're not using x as our variable, we're using t as our variable, so this represents the time. So it's going to take 3.25 seconds to reach the maximum height, and then we want to find that maximum height. So we're going to calculate h of 3.25. That's -16 times 3.25 squared plus 104 times 3.25 plus 8. And let's get our calculator to work that out. Okay, so we're going to work this out. In the calculator, we have -16 times 3.25 squared plus 104 times 3.25 plus 8, and that's 177. So that is our maximum height, and our units are feet. It also says here, feet. So we're going to, our toy rocket will reach a maximum height of 177 feet, 3.25 seconds after launch. Thank you for checking out my videos. Have a great day.